Welcome to a new test and teardown video. Here is my Fluke 5200 Programmable AC Calibrator. Yeah, I got this one a few days ago and I'm a little bit excited about this one. It is a very, very big unit. It's 24.4 kilos. I just put it on my scale. It's released in about 1975, and back then the sales price was $12,000. So, that is a lot. I also got the full manual, including all the schematics. So that is pretty good. Look at that. All the fancy-pantsy things in a paper version. It is in a little bit of a sad shape. And of course, I know it is not working. So what else can I say about this one? I also scored the power amplifier. The 5215 a power amplifier, but I will put that one in a separate video, so stay tuned for that one as well. Here is a super brief product overview of the performance and its resolution, and look at that, there is a range with 1 nanovolt resolution in the 1 millivolt range. I mean, it is just, of course it is like that. With all those digits, yeah, this is the kind of resolution you get, and all those ranges and all that. It's just fascinating. So before I go open this one, I just wanted to show a few little minor status things about this unit. And of course, all those many dials, they work really, really nice and fine so far. And up here, you'll see there is a really, really cool mechanical solution. Look at that. And then you dial down here, and then I love the way they have solved all this. And there's of course one more here that is doing exactly the same. I mean, you gotta be impressed. And here we go with the kilohertz, and then look what happens with this one. Don't you just love the way they figured out to do all this? So millivolt, volts, and no kilovolts, but millivolts. So that is a 1 millivolt range, and here is 1 millivolt. I bet there will be a decimal lit up here, and then you get all those digits. Or is it? Yeah, 1 millivolt. Oh my God, that is so cool. And the frequency range is all the way from 10 hertz, right? And you can go down to, yeah, see, 10 hertz, and that should of course be a 0 or a decimal point here, and then go all the way to megahertz. And it's only, I think it's only 1 megahertz. It also says here 1 megahertz. And I got a few more problems, and that is those switches, they work nice and fine, but the operate is locked. So is this locked due to we don't have any power on, and that means we got some relays and mechanical locks, or is it simply just because it is stuck? And some of those Fluke instruments that's like really dangerous or high power, high voltage stuff like that, I mean, I think there is some sort of relay and protections and stuff like that. So that is why I don't want to pull this one real hard before I know a little bit more. You could of course also just start reading the instruction manual and figure out if this is true or not, but I'm going to open it anyway and investigate the status of this unit. So there's supposed to be some sort of a little cover here, and now there's access to a little circuit board edge connector. This one is wired for Europe power, so thanks a lot for that. And yeah, what else have we got? Also, this one is with the optional IEEE interface, and I'm also a little bit happy about that. And we got a little bit of frequency counter outputs and all that kind of stuff. And you just pull somehow to remove the filter. Maybe it's just here. Oh, that sounds pretty easy. Okay. So that is nice and clean. And of course I want to show the view here from the back, where we can see the little indicator wheels and the way that stuff is mechanically connected together. So we need a little bit of light here to show that. That is so cool. Yeah, that one. Yeah, we got a few screws missing, and that is of course no surprise. I got this one real cheap. I definitely expected it's not working. High voltage warnings about all that. And we got everything here. It's written nice and clear what to measure for and what to adjust for and all that kind of stuff with the top lid mounted. So this is my first little view inside this unit, so let's do this together so we can all see what is going on. And the first thing that I see is the green connectors for the different plug-in ports. The first three, they are broken at the top. So this looks like somebody don't know what to do. And as far as I can see, those different plug-in modules here, of course you need to loosen some screws, and then you can pull them back and see you got the distance here. And then you pull them back and then you pull them up, and there's even stuff to grab, because this one is big and heavy, and there's stuff to grab, and then you can easily just lift it up. So why did this happen? Did somebody flip this around, unscrew all the screws, and then the weight just made it go like this, and then crackety crack? I mean, this is of course not how you're supposed to do this. But what do you know? This is a little bit of a problem, I think so. And here, look at that. Well, that's a big, hefty hold and carry and pull here, because this big hefty transformer is of course more or less it's probably half of the mass in this unit. That is, ooh, this one is nice and loose. Okay, we got a little screw down there and stuff like that. So I think I will carefully see if there's any way that I can rotate this one. I should probably put on the covers before doing so, and I think that is one of the problems with this unit. It's a little bit, you need to know stuff before you just poke around here. So here is this operate and standby switch, and now I can move it. All I had to do was to lubricate the whole spring system, and there is a very thick spring in here. So it takes a huge amount of force, and somebody put in some sort of a grease that turned itself into chewing gum or something like that. But now everything like that is cleaned away, and now I can move the switch real nice and fine. Haha, how about that? All the other switches, they operate pretty good and fine, so that is fine. I really want to show this little detail here. This is the voltage error compensation and calibration kind of circuit. And the idea is you can turn this on, and then you have this little switch here, and you can operate this and calibrate. But look, it's made so it's completely flat here at the front, and that is due to this indicator here being rolled up on two rollers. And also look at the angle this dial got. So let's look in here. Here is the multi-turn potentiometer for this feature, and we can probably, we can almost, just look at that. We can almost see what is rotating. Here we go. Why is it so much out of focus? Annoying. Here we go. In here something is rotating, right? And also down there, that will be the two rollers, and there's a little gearbox that also operates the potentiometer. That amount of mechanical engineering into making one simple little feature, isn't that just lovely? So I took out all the units from this box, and it isn't really that difficult without breaking any of the connectors. All you have to do is just pull them out straight. And there are, of course, these little plastic steering thingies here that makes it quite easy to hit the exact spot of the connectors. So I really don't understand why this happened. Maybe somebody flipped the unit over. That you're not supposed to do, of course. And here is the power supply. It is enormous. Also, remember, this unit can only do about 200 watts or something like that. It's only using about 200 watts, right? So, why have we got this, I don't know, half a kilowatt transformer, maybe even more, isn't it? It is so big. And the power supply is very, very complex. We got a lot of the rectifiers, and here we got some more of the regulators. Down here we got some more rectifiers and capacitors. I can see some parts, see down there, they were replaced and repaired. I also see some capacitors changed, and everything looks more or less okay, but I do see some tantalum capacitors. I'm always afraid of those. So let's just pull the connectors, and here we got the little rectifier board here, and a few of the supply voltages, and then here we got some more of the supply voltages. They got high precision wire wound resistors right there, and a few of the components, they run a little bit warm, but that's just the way it is. And of course I got the schematic so we can enjoy this. Look, 8 rectifier bridges, and a plus and minus 15 isolated return for that, 5 volt, and everything is with individual returns for everything. And of course they're doing it that way. This way you have full control of all your different voltages and the return path for everything. Well, what I really think is the most important to remember about this schematic here is this 30-second delay, and this one is the one that handles the standby features. So we know when we power this up, nothing happens, well, just except all the capacitors and all the voltages being powered up, but then all the outputs and the enable for this and that happens after 30 seconds. And here we got plus minus 300 volts, and that is for the output amplifier board. So here is the output attenuator board, and it is quite interesting. We got 3 different transformers for the outputs, depending on the frequency, and obviously the big one is for the lowest frequency bands. And all those different relays, they handle the inputs and the outputs and the tappings of the different windings of the transformers, because this is an AC source. Just to show a little bit about the schematic, we can see here is the input from the power amplifier, and then it can be routed to all the different transformers, and look at all the different outputs. It also says a little bit about the millivolts and all that with the different voltage ranges, and of course you can go to the voltages and skip the step down. So this is a good way to do the different attenuations versus frequency using transformers with tappings. Aren't you a little bit impressed? But that has something to do with the frequency range that goes really, really wild, but also the capability to deliver some power. Well, not a lot of power, but a little bit of power. So you can't really do this with resistors, and that is why they did it this way. And of course we got 2 pages of schematics just to do this. So all the relays, as you can see here, they are controlled by drivers and decoders and the decimal converter to handle all this remote controlled using the different ranges of output power and all that kind of stuff. Here is the next module in the row, and this is the output amplifier board. And I don't know if you can see this white, really weird corrosion that is going on here. And if I touch this and smell my fingers, it smells like blown up capacitor. So, I mean, this acid kind of corrosion all over the amplifier, and this is running plus minus 300 volts. That is definitely not good, and it will lead to all sorts of weird things. And we also got probably those where the capacitors, so somebody changed C23 and 20, and they put in 3 capacitors in series on a 200 volt rail. All the power transistors here, they are mounted on a really nice and thick heat sink like that, and they are, as I can see here, I think that'll be some sockets. So I have a it is possible for me to disassemble this and clean everything here. And look at that, we got some extra little funny things going on here. A little bit of maybe a add-on board. Did they really design it like this in the first version? It is hard to imagine, isn't it? And this nasty corrosion that I'm talking about is also on the other side of that board. So that is something I need to worry about. Oh, the circuit board is nicely, look at that, solder mask underneath this little area, but not on the rest of the board. Why not? How stupid is that, really? And here is the circuit diagram of this output amplifier, and this looks a lot like a conventional audio amplifier, of course. So here is our output, and you see here this little push-pull sort of system, and then it goes all the way to 300 volts here and 300 volts here. Nothing super surprising there. This is probably working, let's hope, because look at that. It is a lot of transistors and a lot of long signal path, and this one is a 10 hertz to megahertz amplifier. So that is probably why it is this complex. Oh yeah, about those capacitors. Here, it is the 190 volt raw. So it's probably unregulated or anything like that. So here is a local little power supply, and then a little load, a minimum load for this, and a current regulator for that, and there you have it, your 190 regulated for some small stuff that is needing that. Here we got a 90 limit, blah blah blah, and another 190 here for that, and there's also another regulator almost looking like that, and here is the other one of those capacitors they replaced. So this is the power amplifier. After a lot of cleaning, I really tried to get all this off. I washed it with hot water and soap and everything like 3 times, and then I washed it in alcohol a few times with paint brushes and compressed air and whatnot, and then I ended up adding a little bit of varnish to the, you can see it shines a little bit here, to the areas where the tracks, they have been mostly attacked by all this funny weird corrosion. And yeah, so I think it is more or less okay to power up. Now I'll try and reassemble everything again, and now we can of course see we can also see the back side of this board, and this really weird area where they put on the solder mask instead of adding the solder mask to the whole board. Yes, I also add a little bit of varnish here on those really badly corroded area. So here is the power transistors, high voltage and a little bit of current, and there you have it, a lot of heat, right? Isn't it a little bit funny about those two transistors? So the original design, they'll just be some normal transistors, right? But instead of changing the entire mechanical design and everything like that, then they figured out that they wanted some other transistors instead. So 4 paralleled transistors. So this is actually a homemade 4-in-1 parallel transistor thingy with little individual emitter resistors for current sharing and a little ferrite. Isn't that just a cute little plug-in? And see, they made it transistor compatible. So we put in 2 of these, and they are of course exactly the same. Are they? Oops. Look at that. I see some different colors on those transistors. And this one, we got some other transistors. So, oops. I better go check. What have I done here? Oh no. There's probably a good explanation about how to put these back, but oh yeah. So here we go. This is, let's remove these 2. That is something I did not see coming. So Q20 something, I can't see anything with this reflections here. But I better go and check this out. Okay, I added a little info here. So Q23 is a PNP and Q20 is an NPN. So that is the difference with the little colors here. And let's look a little bit again in the schematic. Here we go. See, Q23, and that is the PNP. And here is Q20. That'll be an NPN, and here we go. Multiple transistor AC. And there's one little extra detail that I figured out. It's actually written here, really difficult to see. Q20. And the other one, somebody wrote this. Here we go. Hey, where are you, little friend? See, Q23. Not easy to see, but that was important. Here is the AC DC converter, and I think it's actually a wrong name for the unit. I think this is a DC servo that makes the output always 0 volts, no matter what the amplitude and what the frequency is. I'm not exactly sure about that, but that is just what I think so far. But let's see if I'm wrong about that later. Probably I get smarter. I did take it a little bit apart so we can see the different details here. We got some op amps, and those op amps, they're actually a little bit special. So let's try and look at one of them. They're a little bit different. We got some resistors here for some gain settings and stuff like that. That's more or less all. But look at that down here. We got Q3 and Q2, and then we got an op amp. So what have they done here? Adding extra transistors to the input side of the op amp to give it some special properties. So I think that is quite fascinating. And then again, they added a little thermal shield here on top. This looks like it is heat and vacuum formed. And I have seen Fluke using exactly this design before, because in my DC calibrator, this is exactly the same cases they're using. So that is a little bit funny. And they're using high quality, high priced components all over the place, as you can imagine. This little cardboard tube here, that is so you can reach easier this trimmer that needs to be in this area. Here is a critical high impedance and high gain sensitive area. They cannot have the tracks to go all the way up here to put the trimmer where it's easy to access. So this little tube here is so you can stick in your screwdriver, and then this is a steer for your screwdriver, so it's not touching anything other than the trimmer. And that is a pretty funny way to solve this little thing, don't you think so? And here is my schematic for this AC-DC converter system. And there we see some different amplifiers. They call this rectifier amplifier, because this one is an AC to DC or ideal diode. And then we have, look at that. That will be the Q3 and Q2 input transistors before the op amp. That is one amazing coupling to get some special properties out of this. Oh yeah, and again, we've got some different input bits and all these different things. This is amplitude and limit settings and all sorts of things that changes during the different voltages and frequency settings. And there you have it with some switches that is changing the properties for this entire circuit. And this board is called oscillator control, and what I think it does is it takes some of the oscillator signals in and out using those SMB connectors up here, right? And if we look at the relays, that is controlling some different filters. So I think this is just some filters, because if we look here at the schematic, we got some phase lock input. So yes, of course, it can change to an external clock. We got the oscillator input here, and then it's generating all the different frequencies and dividing this and that here. And look at that. That will be some different filters. All of this is controlled using some relays, and those relays are controlled again using a little BCD decoder. And here you go, that will be the different ranges, and that is handled using some BCD signals. Isn't that fascinating? Just to save signals from the switches and all that kind of stuff. It also says here the different frequency ranges, how this is handled, and then it just activates the different filters, and out comes the cleaned up signals. And here is the oscillator board, and look at that, a whole lot of transistors, and that is for selection of all the different resistors and capacitors and everything that is needed to select all the different frequency combinations. A digital input variable programmable oscillator. I totally love it. They've done everything they could to make it look as nice and fascinating here with the different. I mean, let me show the schematic, and then you will see what I'm talking about. Here we see all the different values and all the selection transistors. So of course there's a lot of bits input for all the different frequency bits. Look at that. See? Frequency. That will be the first decimal, and the next, and the next, and so forth to handle all this. So you see, yeah, digital input system, and then these signals here, they select all those components here in this oscillator system, where we have, of course, the capacitors and the op amps and everything like that located. Summing amp, we got a 10 hertz to 1.2 megahertz. And here is my IEEE interface, and it's actually isolated. And I think that is super, super sexy. So there's a power supply, isolated power supply for the microcontroller. See, this is a UV erasable and reprogrammable microcontroller. They put in a little sticker here. We could just remove this so you can see there's a little quartz glass, and then you can see the little microcontroller in there. So the memory area in there will be erased by ultraviolet light, and then you can reprogram it. Anyway, so this one handles the IEEE communication using optocouplers. It pulses all the settings into some latches and driver systems here, and this activates all the transistors here that's driving everything in the unit. So these actually controls that is how many bits we got to set the voltage and the ranges and the frequencies and everything. That is how it works. And I really like the way with the little wall here, and I mean, they mean business with isolation and noise and all that. This is a little bit fascinating, isn't it? Here is the IEEE side of the, this is the connector, the business end, where we got the 8 bits, and then you put in some addresses and clocks and whatnot, and this way you can write into this system. And then on the other page here, let's move this one, the microcontroller latches and stores everything, as we can see here, and it drives this one, and then it goes via the optocouplers, bitty big banging, all those drivers, and there you have it. That will be all the signals needed to handle all the different frequencies and amplitude, this and that, and of course it is, I think it is probably latched somewhere else, so you get these bits one more time, because you need all here. You can see it's just frequencies, but you will have them one more time for all the amplitudes as well, right? But that is the remote controlled interface using IEEE. And this is the last module, and it is looking very secretly shielded and double shielded and all that kind of stuff. Look at that. We got a circuit board in the middle, and we got another shield board on each side, and again it is specially made with some copper on one side and another side, and then there's a wall that is not connected to this, but it's probably connected. Yeah, it's connected to some of that. And then, I mean, what the heck is going on here? This is some fascinating stuff. And this is the up side, and then this cable here goes to one of the other modules. This is actually, I marked it with green paint so I can know this is module number 5 that it goes to. And here, I think we should open it as well, but this is just the first little component placement. So we got a lot of transformers and super isolation transformers between the two walls where they go. I mean, this is super, super special what they're trying to achieve here. And I tried to look a little bit at the schematic here to get a little bit of an idea of what to expect. Yeah, look at that. We got 2 transformers and a little extra winding in here to make it super, super isolated. And it also shows there's a guard and an inside and an outside and all this. And then this signal here is flippity floppity fed amplified. And then there is a super, what the heck? Superstar ground and an extra amp era amplifier. And here we got a 5-pole active filter, and yeah, so there's a variable reference. And this one, oh, we got another one. Here we go. So the switches for all the different settings from the switches, right? Sets this and this and this. And then you can either be in remote or local. So here is how this is switched and buffered and all that kind of stuff. And then all these signals drive all this and divide and count and count and count. And up here is a 10 megahertz oscillator. And the fun thing is, it's not a crystal oscillator. It's just a free running oscillator. Obviously super packed into a little box of its own and all that, but it's really not even a crystal. Come on, guys. And then there, all this output and then driving this and that, and here you have it for your super isolated. Yeah, I totally love it. They really did a fantastic job here. And of course they put the little oscillator out here, and there's a ref adjustment like that. Yeah, I think we should definitely open here and have a little look. I think the reference is a whole new level of fantastic things. I've been laughing the last few hours reading the schematics and trying to figure out what are they doing here. But you gotta love this construction with the extra wall in between the 2 rooms here. And this is where they transmit the AC signal completely isolated as much as they could possibly do it. I can't remember I've seen anything like this before. And Fluke, they are just the best of the best when it comes to stable reference equipment back in the 80s. And they also made the famous DC calibrators, of course. Look at the way that double walled all the way. And here's, of course, the top shield to close everything here. Look at that one. Just to figure all this out is just definitely something. But anyway, I think we should look a little bit more at the schematic as well. And if we zoom in here, you can of course see some super nice precision components. Look at the start point, and I actually don't even want to touch the resistors right there. So those super precise, insanely expensive resistors you see here, they are a part of all the op amps and all the feedback and all this system here. It all comes down to this part that is important. And I think we should maybe look this up. It is called the SZA and then 263. And it's from 1980. That one is a super precision voltage reference. It's a Zener diode and a little transistor. And the thing is, this Zener diode in there is about a half a ppm per Kelvin. It is that crazy in reality. So yeah, now we have a super stable, accurate voltage reference together with those op amps, and this is probably in the feedback and amplification system here. And of course they're using some op amps of the most fantastic style they could find back in the days. And then we got the little AC oscillator, and that is all that stuff that's driving this 10 megahertz. And then we have all the divide down to this and divide, and then programmable interfaces to divide and set up all the different things that we want.